just got two of the cutest things. Don't worry about it. It's not a big deal. I was just making conversation. Hey, Carter. Hello, Carter. Did you think I wasn't showing up?
There you go. I was trying to say how you feeling, but my thing was on mute. I didn't even know it.
Gotcha. Yeah, well, the back pain's not as bad. I don't think anything actually happened though, so I'm not sure what's going on, but I know I can teach from a Zoom standpoint at least, so I figured I better do that. And
Gotcha.
at least that way I won't miss more material and the updates on information regarding the final and all that good stuff.
Right, right.
So
Um, I did send you an email. I don't know if it's just me or what's happening, but I remember how I had that weird thing with the last practice test where I only got the first two problems and the rest of them were blank.
okay, did that do it again?
It did for the online test number 7 this time. So like I only have two questions in it.
Oh, Jesus.
Um,
That's
so
jacked up because today's the day.
yeah, I sent you an email about it, but I knew you weren't feeling well. I didn't want to bother you.
Gotcha. I have not been as well, not even as attentive as I normally am regarding that, but I will fix it immediately afterwards.
Okay.
And yeah, I'll try to if you can help me remember. Let me tell all the other students too that I'm going.
Yeah,
I'll probably remember, but just in case, keep an eye out for me if you don't mind. I would
absolutely.
greatly
Yeah,
appreciate it.
I haven't taken the face to face because I wanted to take the online test just for practice and stuff first. So
Gotcha.
um, I know the face to face is due today too, but I'll just do that after this.
No
Um,
problem.
and then, uh, oh, I had another question for you. I got your email today about redoing the test work,
Hmm.
um, and it would be under the assignments tab.
Uh, yes. Well, it might be under your assignments tab. I just put it in the lowest weekly module
The
meaning
lowest
lowest
weekly.
on the Canvas page. I just stuck it in there.
Got it. I
And
see it
then
now.
you see it now? Okay.
Yeah,
I
under
also
it's
had a
under.
couple students report that it was in a hidden module, so it was making it hard where you couldn't get it.
Yeah, I see it now. I just didn't see it before because I was looking for like announcements or whatever, and so I just didn't see it before. But it's under for me, it's under lab accoutrements, so I see it now.
Gotcha. Well, this is aggravating.
Okay.
I'm just looking at the chat online test 7, and that really is aggravating. Literally, it's only the very first question, so I've got a lot of work to do to fix that. I was going to do it in real time since I was waiting for people to log in, but it's way too much to fix right now. So I'm glad you found the place to turn in this stuff. I guess we'll go ahead and get started, even though it's only 3 of you here. I wanted to get some stuff on the record to make sure everybody knows what's going on. So I assume y'all can all hear me, right?
Hmm.
Okay. Were you getting ready to say something, Carter?
No, I'm actually I wanted to read the
The emails?
assignments for the redo test. I hadn't seen it
Okay.
yet, so I was just trying to read that. Sorry,
Gotcha.
I can put it on mute.
Gotcha.
Sorry.
And that's a good problem solving profile or I don't know, model or whatever. It's just how I said you write the question, you write the answers, then you write the solution. You start off with solution and state equations are principles you plan on using, state, that kind of stuff. So I gave you some more descriptions that are probably more than you need, but I think those are good enough that they could be used for any physics, chemistry, or engineering class and probably make your grading life a lot better for instructors to grade you better. All right, so let's get started. I'm going to turn on my iPad in a second where I've got some notes about what to expect and what you're expected to know. So I started thinking, I was going to try to fit in some more material and maybe cover some more lectures. I was even going to send some lectures out over the Thanksgiving break. At the end of the day, I just decided that that was going to just stress y'all out and make things really horrible for you. Uh, I'm feeling really bad because really I should have gotten through chapter 31, which is what I normally do as a bare minimum, but I didn't get that far. But I'm not completely upset because I've given you access to all those homework sets where you could, in principle, learn the material if it's really important to you. Uh, so I've tried to figure out some kind of way of feeling better about what I'm testing you on, but also being fair and not making y'all grow great hair and want to, put bombs in my car or anything like that. So what I decided was basically we've already covered all of chapter 25 and essentially very much of chapter 26. That being said, I'm not counting chapter 26 or any later chapters on the homework except as extra credit. So if you get a 70 or higher on chapters 26 or later, then I'm going to automatically just give you 100 for that homework set. That being said, I don't want you wasting a lot of time on your, well, quote unquote, wasting a lot of time on your homework, except maybe after you're done with the course. For instance, once you finish your final exam, if you want to go back and solve problems, that's great. You don't need to before the test. The most important thing for the final is that you, for one, redo all the face-to-face tests that we've had, which for you guys, that's 3 of them. And I've created a module in the latest and the lowest positioned Canvas weekly module. In that module, I've put 3 assignment redo uh, places where you can turn in your assignment. And inside it, I gave you very explicit instructions about how to conduct that uh, face-to-face test redo. So make sure you follow those instructions or you're liable to get no extra credit points. My plan is to give you extra credit on your face-to-face test based on that redo. But really, I'm not going to spend a lot of time grading that or looking at every detail to make sure you did it correctly, because this is your chance for you to learn how to do the problems that you, in many cases, didn't know how to do. And if you don't take me up on that, that's on you because it's going to kill you. Okay. The final exam is going to crush you if you don't know how to do that stuff. So what I did was again allow you to redo that, which is an excellent opportunity for you to learn. I'm going to figure out some way to give you credit on those old face-to-face tests, all 3 of them, and then I'm going to drop the lowest face-to-face test as I had promised. But still, you're not going to get any credit unless you do all 3 of those redo tests. Okay. Once you're finished doing those redo tests, then your only objective should be doing the practice test over and over and over and over again. Now, Carter just mentioned that I screwed up something on online test 7. So I'm going to put that date another day back, and I'm going to put the face-to-face test. I'm going to put that back as well another day, basically till Thursday instead of just a Wednesday, because I've had all these problems with my own health and all that good stuff. So I'm going to push those due dates back for anybody that still hasn't taken their face-to-face test or their online test. Not only that, online test 7 is messed up, so I got to fix it. So I'll do that, and that'll be fixed right after class. But like I said, the main thing you should do once assuming you finished your last face-to-face test and your online test 7, once you finish those, then you should be only focused on redoing those tests and learning how to do those problems. I'm talking like get together study groups, use Chegg as much as you want. And to be honest with you, some of this is going to be you just memorizing the way to solve the problem, because that often is the lowest tier of learning, and you've got to sort of memorize a way of going about solving a problem. And then because it's memorized over time, you might actually slowly start to understand it. That's the ideal scenario. So it doesn't always require that, but sometimes it does, especially if you're just, consistently making bad grades on physics. You got to memorize a bunch of stuff until eventually it starts to click a little better and you can solve other problems that aren't exactly like the ones you solve. So that's what you got to do. Once you're finished redoing all those 3 tests and then turning them in, they're due, by the way, the day before your planned final exam. So for this class, your planned final exam was supposed to happen basically around this time, 5:20 p.m. on a week from today, which would be Tuesday. That being said, I'm making a whole series of test due dates for my face-to-face class as well as for my online classes. Generally speaking, your exam or your lab instructor gives your final face-to-face exam, and I suspect your lab instructor will have a particular day that they've planned on doing that. Please let me know what day that is, and that's fine. I'll make sure that happens. But I'm also giving some more time where you can come in and do it in our labs on the Virginia Beach campus. And I will have a litany of times on Monday and a litany of times on Tuesday and a litany of times, or at least a partial list of times for Wednesday. I won't be able to go as late into the day as I do for Wednesday, as I did for Monday and Tuesday on Wednesday. So you will have your choice of taking the exam on Monday, on Tuesday, on Wednesday, plus whatever your exam, your lab instructor is doing. I've got to, again, speak with your lab instructor to find out. Do you guys have Miss Raskovic, or do y'all have our new guy? His name just escaped me, so I
We
can't.
have Dr. Johnson.
Dr. Johnson, gotcha. Okay, that's cool. So yeah, I'll make sure I check with him. Has he mentioned anything about any more meetings for y'all?
So we don't have any more face-to-face meetings. He, if you have a 90 in the class,
Uh-huh.
you or higher, you don't have to take the final
Lab final.
exam. If
Gotcha.
you need to take the final exam, it will be posted online. I'm not really sure. I think it's supposed to start Thursday.
Okay.
I'm not really sure.
Okay. I'll contact him then. I was just hoping he might have said something to you. I haven't seen an email from him, but really I've been down for the last day or two. So anyways, now what I said was anything beyond chapter 25, you get extra credit for doing those assignments. But there's also very specific topics that are still, to some extent, going to be covered on the test. And that's what I took all that time to create this final exam that's extremely limited on chapters 26, 27, 28, and 29. I ended up cutting out 30 and 31. It was originally called a test through 31 where I had taken little bits and pieces, but I really only did it up to 29. And it's very simple, straightforward stuff. You'll see as you're doing it, they should be some of the easiest problems. And it's not even necessarily the case that I'll be covering all that stuff on this comprehensive final. It's more a matter of me seeing that you've been doing this with the final exam practice so that I feel comfortable with saying, okay, they've got an understanding of chapters 26 through 29. I feel like I'm in a good place with the tests that I make them. So there might be some simple questions on there from that material, but and that's what they are. But they're exactly like the ones that you see on this practice final. So everything you see on this practice final, no matter how many times you take it, everything you see from chapter 26, 27, 28, or 29 will have come uh, exactly from that practice final bank of questions. Now, I'm toying with the idea of doing a non-multiple choice final exam. Okay, so that's why it's very important that you guys learn how to do those face-to-face test one, face-to-face test two, and face-to-face test three. Make sure y'all learn how to do them because I might just take some of those questions and render them non multiple choice, change a couple numbers, and then ask you to solve them. And of course, if you just memorize how to do them, that's not going to help you very much. Okay. The memorization of how to do them could help you if you're really wicked good at memorizing and therefore can just replace the correct numbers or the bad numbers with the correct numbers, then it might work out for you. Okay. So that's the whole thing. I need you guys to do those 3 redos for the face to face tests. Then I need you to hit those practice tests over and over again. And now I'm going to go ahead and show you what is critical of that remaining material from chapters 26 through 29. So let me turn on my iPad. Does anybody have any questions while we're doing that? The redos are mandatory unless you have an A average. Let's put it that way. If you don't have an A average, meaning all of your face-to-face test scores are a 90 average or higher, then I'd say no. I won't allow you to not do it. If you don't do it, you're just going to get the grade that you had in the in that, and none of the extra bells and whistles that I offer in my class will be available to you. So that's sort of the short question of that. But yeah, I realize there's on the order of 4 or 5 students that have done really well on all the face-to-face tests and stuff like that. Send me an email privately, Giovanni, if you have a question about that. I have some very specific statements I'd talk to you about. So, uh, anyways, or send me a text. That'd be even easier because I'm still kind of sick and I'm not sure how often I'll be able to check my email, but I'm definitely be checking my texts. All right, so now I've got my iPad on and I'm going to share my screen with you so I can point out some specific stuff that I'm going to hold you responsible for in the course material for chapters 26 through 29. So as we wait for that, it'll come up in a second. But anybody else have any other questions? Okay. So
Oh,
I've
I
written a
was
lot of,
wondering,
yes,
sorry, Professor
go
Garrett. I
ahead.
was wondering, did you receive my text message from earlier?
I received a lot of them, but I've been answering like every 2 seconds. So I might have, let me see.
It's
Oh,
so,
yeah, see, you got that was back at 3:46. Yeah, it's the fourth one left of me to answer. So,
okay.
is it something that I need to address right now or what?
No, we could address it afterwards. It's just the
Oh,
online one
actually, yeah,
is
that's exactly what I was. Yeah, you're exactly right, Tanika. That's the same thing that happened with Carter. I've got to fix that right after, and you
okay.
might not have been in when I announced it, but basically earlier I said that I'm going to push the online test 7 and the last face-to-face test to be due on Thursday as opposed to the night at
Okay.
11:59, and
That
that's
works
because of
perfectly.
that screw up with that test.
Okay, thank you.
You're welcome. Thanks for asking and thanks for sticking to it and helping me stay abreast of the stuff. I do appreciate you guys' texts. I know you probably think you're offending me or hurting my feelings or making me mad. You're not. You're really helpful. I appreciate that. So let me read this to you. I did write it in cursive, but the homework for chapters 26 or later are extra credit. If you get a 70% or higher, you will be awarded 100%. If you do not complete one or more, there will be no penalty. Okay, that's what the multiple choice, or excuse me, that's what the extra credit on chapters 26 and later means. You also need to know the following material. One, how to solve circuits. So that was like the last problem I solved in lecture last time. We solved a pretty complex circuit, not that complex, but pretty complex DC circuit. There's a ton of examples which you can get by going to my YouTube channel and doing a search for Kirchhoff, and you will find a ton of other examples of me solving circuits. There's more examples in the book. There's more examples, of course, of me on video doing it, either with an iPad or by handwritten notes, all that good stuff. So that's one thing you got to be able to do is solve a system of equations by, or actually more specifically, solving a DC circuit for all of the currents in it by using the techniques. Specifically, what I teach is Kirchhoff's loop rule and Kirchhoff's junction rule. But I know there's other techniques, and I don't care what technique you use, long as you can do it correctly. So I do need you to be able to be able to solve those circuits and to solve the system of equations that comes out of trying to solve those circuits. So that's a big thing. Oh, I did see someone's comment on my YouTube channel today that they were going to play a drinking game. Every time Mr. Younger yawned, they were going to take a drink. So I just thought that was funny. I should tell you, I appreciate it. Number two, identify and use Gauss's law for the magnetic field, Ampere's law with, actually, I said with Maxwell's correction, and Faraday's law. So those are the three things, or those are the four equations of Maxwell. That is the crux of this course. So I expect you to be able to identify them and use them within a limited context. Obviously, we've done a lot with using Gauss's law, so that's certainly fair game. There's a good chance that you're going to have to use Gauss's law to compute electric field, then use V equals a negative integral at E dot dl to calculate the voltage between two parts of a capacitor, and then use C equals Q over V to compute the capacitance of a capacitor. That's a 3-step paradigm that I've been teaching you the whole semester, and I've yet to take off points for people not doing that part of their test on the face-to-face test, but that will definitely happen on this final. So you guys got to learn how to do that once and for all, even if it's just memorizing. And again, you can find 1,000 of those on my YouTube channel. In that case, I would recommend you do a search for Paradigm, Paradigm, Paradigm. So that will show you how to use Gauss's law to solve for a capacitance of a capacitor. All right. Number 3, it says know how to calculate magnetic forces, and I gave you the 2 formulas that you got to be able to use: F equals QV cross B, and DF equals IDL cross B. And then 4, the law of Biot-Savart, which I'm getting ready to demonstrate for you as well. There's some really simple problems that you can do from that, and you need to know how to do those, and I'm going to demonstrate that for you. And there's one hard one that we're going to show you, just so you'll have the experience of seeing it. In principle, I could ask you to do that as well. I don't know that I will, but that is certainly a fair game for a comprehensive 242 final exam. So again, with all of these 4 topics that I pointed out, what you can do is use all of my past lectures. You can also ask me questions. You can send me text messages. You can send me photographs of problems that pop up on your practice final exam, and all of that I can use to help you. But you've got to figure out how to do these things at the level that you see in the practice final exam, which has been posted. Now, what I said after the list of 1 through 4 is search my YouTube channel for Kirchhoff, Biot, Amperes, that's Ampere apostrophe S, Faraday's, that's Faraday apostrophe S, and magnetic for videos on those topics. I would also say the word paradigm, so I'm going to write that here too. That's supposed to be an A, and actually, oh, I took my glasses off, so that's why I can't see. Well, now it looks really crooked the way I got it on here. Oh, that's not helpful at all. There you go. Okay, so I was writing the word paradigm. Okay, so do a search for that one as well. And then I said at the bottom, after redoing your face-to-face test, you should only focus on the practice final exam, because that's the most comprehensive and helpful thing you can possibly do. Of course, that was under the assumption that everybody had already completed their last face-to-face test and their last online test, but I see that that is not the case. So make sure you get those done and then proceed. Anybody have any questions on this list here? All right, so let me state those laws for starters. So, whoa, did they? So, for instance, we have Gauss's law. That's the closed integral of E dot dA is equal to Q enclosed over epsilon naught. We also have Gauss's law for magnetism, or Gauss's law for the magnetic field. That would be the closed integral of B dot dA is equal to 0. And basically that is interpreted to say there's no magnetic monopoles. So for instance, if you take a magnet that's, got a north end and a south end, and you cut it in half, what happens is one half becomes a new magnet with a north and a south end, and the other half becomes a new magnet with a north and a south end. If you cut those in half, the same thing happens, up until you get so small that really no magnetism is left. Okay, so there's never a point where you can cut it in half and get a south pole or a north pole of a magnet. So that's Gauss's law, and Gauss's law for magnetism. There's also a Faraday's law, and Faraday's law basically says that the induced EMF E is equal to negative N d phi B over dt. That is Faraday's law, and that's often written with a closed integral of E dot dl. So you can also write this as the closed integral of E dot dl is equal to negative n d phi b dt, and phi b is equal to the integral of b dot dA. Just like we had with Gauss's law for the magnetic field, we have for an electric field, we have a magnetic field and a magnetic flux given by B dot dA, just like we had a electric flux given by E dot dA. Okay. Now we also have Ampere's law, which for right now we're just going to state as the closed integral of B dot dl is equal to mu 0 I enclosed. So that's Ampere's law, and I'm going to show you how to use that in a bit, but I'm also going to tell you that later on, Maxwell is going to make a correction to it, and I'm going to try to remember this off the top of my head. I'm not used to using these systems of units, basically, so there's some chance I might make a careless mistake, but you can look it up in your book. I think it's mu 0 epsilon 0 partial derivative of the electric flux with respect to time. And I think that might be the magnetic flux. Let's see. No, I'm pretty sure that's it. But anyways, there's an extra term that's supposed to be added to Maxwell's or to Ampere's equation specifically to make what's ultimately called Maxwell's equations. Maxwell did that. That term's called the displacement current, and it doesn't really mean anything, so ignore that name. It's not a helpful name that would, help you better understand it or anything. But it's something like that. So I apologize for not looking it up. I wasn't planning on writing them here, but I figured I better now that I have everything laid out on one page. So let's get started by showing you I'm going to show you Biot-Savart law as well as magnetism in general. So what we're looking at now is chapter 27, which is on magnetism. And in chapter 27, a couple things they tell you are the following. First, they tell you that a current carrying wire creates a magnetic field that is perpendicular to the current direction. Imagine a long, straight wire that is perpendicular to the current direction and coils around the wire in a direction given by a right hand rule. Now that magnetic field is given by a magnitude B, which is equal to mu 0 I over 2 pi times R, where mu 0 is equal to 4 pi times 10 to the negative 7th. And that's 10 to the negative 7th Tesla meters per amp. Okay. Let me draw a little picture for you. What I'm going to do is I'm going to draw a coordinate system. Okay. And this line right here, this x-axis, is drawn in 3 dimensions, so that's supposed to be coming out of the page at us. This y-axis is on the page and points to the right. This z-axis is on the page and points up. And what I'm going to do is imagine a wire that's infinitely long and straight and is actually aligned along, is actually aligned along the z-axis like this, so that the current coming out, going through it, I, is going up. Okay. So if you imagine that, then what you can do is imagine this pencil being the wire. Imagine the point pointing in the direction of the current travel. So the current's traveling up the wire. What you want to do is imagine grabbing this wire with your right hand, such that your right thumb points in the direction of the current, like that. And now what you'll notice is your fingers are actually coiling around the wire in a direction. Your idea is to decide whether that direction is counterclockwise or clockwise as seen from your position. Okay. So my right hand, when I do that and I look down at it like this, I can see that clearly that's the counterclockwise direction. So what that means is if I come out a distance, let's say a distance of r equals 1 meter, which I'm going to say is roughly this far, then if I go a distance of 1 meter as well from the origin along the y-axis, then that would be about there. If I do the same thing along the negative x-axis, then that would be about there. And if I do the same thing along the negative y-axis, that would be right about there. Okay. So what I mean by choosing that particular r equals 1 meter distance is by doing that, you'll notice that for a given current I, the magnetic field has a constant magnitude. So by choosing a specific R, I get a line that gives me a constant magnitude, and that line would be a circle. So if I imagine a circle like this going around that way, notice it's going around in a counterclockwise direction, then that's the direction of the magnetic field at, for instance, let's do something really bright here. So right there, that direction is into the board or into the screen. Similarly, that direction back there behind the screen is to the left. Similarly, this one I can't really show that well, but it would come out of the page. So out of the screen. And this one's to the left behind the screen. And then up here, it would be to the right. And that's to the right and in front of the screen. Now, the whole reason that points that way is based on the law of Biot-Savart. And the law of Biot-Savart basically says that a differential magnetic field element is given by mu 0 I over 4 pi times dl cross RP, where P is the point at which you wish to know the magnetic field, minus RDL, where RDL is the vector that points from the origin to the point DL on the current carrying wire, and P, of course, RP, of course, is the vector that points from the origin to the point P at which we wish to know the magnetic field. And then all of this will be divided by the magnitude of RP minus RDL. And this is really a 1 over R squared law, but I'm have to write it as a 1 over R cubed law because the RP minus RDL on top makes it have or be increased by a factor of the magnitude of RP minus RDL. So I have to put it cubed down in the bottom to cancel out that factor. Okay, so that's where all that came from. Does everybody understand what I mean by saying the direction of the magnetic field due to a current carrying wire? I mean, we did see Faraday's Law lab where you got to experience all those compasses around the wire. So hopefully that helps you. But this is basically it. I will also point out that in this orientation or in this configuration, the magnetic field caused by I points in the, well, in the theta hat direction. So if you look in my YouTube channel at cylindrical coordinates, you will find that there is a coordinate vector for the R hat coordinate, or for the R coordinate. There's a coordinate vector for the theta coordinate, and there's a coordinate vector for the Z coordinate. You probably already know the coordinate vector for the Z coordinate is the K hat one, so that's what happens with the cylindrical coordinates. But the R hat vector points in the direction of increasing radial distance R, and theta hat points in the direction of increasing theta hat. So if I imagined a specific point, let's say this point right here, okay, then the coordinate associated with that would be, for one thing, R, which is the distance from the origin to the point, the red dot there. And the other coordinate would be the angle theta, which is measured counterclockwise from the positive x-axis towards the z-axis, or excuse me, towards the y-axis, not the z-axis. And that would be a coordinate as well. And from that, you should be able to see that you get a vector here that points in the increasing r direction, and I'm trying to draw it way bigger than normal. That vector would be called the R hat vector. And then notice it doesn't have any Z components. It's only a function of, say, I hat and J hat. And then in addition to that, and 90 degrees ahead of it, is the vector theta hat, which I've drawn right here. And that too only has I hat and J hat in it. Okay. In fact, you can work it out and you will see that R hat is equal to cosine theta I hat plus sine theta J hat. And you could even find out that theta hat is negative sine theta I hat plus cosine theta j hat. In fact, you probably will realize that theta hat is actually equal to the derivative of r hat with respect to theta. Okay. So notice at that particular red point, that's the direction of theta hat. Similarly, at the red point that's on the y-axis, you can see that the red vector for the magnetic field does in fact point exactly in the theta hat direction. The same thing with the red dot on the negative x-axis, the same thing with the red dot on the negative y-axis, and the same thing on the red dot on the positive x-axis. So does everybody follow that? Y'all have a sense now what direction that is? Now that messy cross product thing with the Biot-Savart law, I don't expect you to know that yet, but I'm getting ready to do something with that now. So are we all on the same page with regards to that? Okay, so there's a lot simpler laws that I got to express to you too. So I want to go a little ways before I jump into the Biot-Savart. So let me point out something else. The Earth, for instance, has a magnetic field. And in fact, the Earth acts like it has a bar magnet inside of it, only the bar magnet is in fact tilted so that it doesn't line up perfectly with the North Pole of the Earth or the South Pole of the Earth. In fact, it sort of points or sort of sits like this. Oops. If you can imagine a bar magnet being right here, this would be the bar. It's completely inside the Earth. And that's it right there. But here's the part that you might not be aware of. The south pole of that magnet is up near the north pole of the Earth. Okay. And I use this mnemonic to help you, so please do. Magnetic field lines are like our aging population. I'm trying to make it more user friendly so it doesn't seem like I'm bashing the older people, our aging population. They leave the north and enter the south. So what I mean by that is the magnetic field line, for instance, from this bar magnet would come out like this and then go back in through the magnet. But the important thing is realizing that the direction of the magnetic field points away from the north and into the south. And that because of Gauss's law for magnetism, we specifically know that the field line never ends. It actually always completes a circle. So notice I drew it going completely through the actual magnet because that's what it actually does. There would be another one here, for instance, and that goes like this, 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 and so on and so forth. Okay. The Earth's magnetic field, B Earth, is on the order of 0.5 Gauss, which is 1 unit of magnetic field, and 1 Tesla. That's the unit we use in the SI system. 1 Tesla is a magnetic field unit. It's abbreviated with a capital T, and it's equal to 1 times 10 to the 4th Gauss. In other words, 1 Tesla is equal to 10,000 Gauss. A MRI, like you use for medicine, is on the order of 1 whole Tesla. And we use some more powerful 2 or 3 Tesla ones for research, but that's pretty much what it is. Okay. Now that we have that information about the magnetic fields, your book does mention, for instance, that the word magnetism came from a place in what's modern day Turkey called Magnesia, where they discovered rocks that would stick together and attract one another and repel one another. So we've got the name magnetism from the place Magnesia in Turkey. And the forces that a magnetic field applies is given by these equations. So F could equal the charge of a particle multiplied by its velocity, and then you got to take the cross product of that vector with the magnetic field. Now remember what that means. Cross products spit out vectors that are perpendicular to both of the vectors that went in. So for instance, the force here is going to be perpendicular to the vector QV, and it's going to be perpendicular to the vector B. And it's going to be given by a right-hand rule where you can pretty much point your hands like this. Notice I have my index finger pointing out. My middle finger can actually point almost parallel to my index finger. It just can't be exactly parallel nor exactly anti-parallel, but I normally keep it at 90 degrees to help me. Okay. And then my thumb is, of course, perpendicular to the index finger, and it's still going to be perpendicular to the middle finger as well, no matter what the position is. Okay. So when you do a cross product, the first vector should be parallel to your index finger. The second vector should be parallel to your middle finger, which again cannot be exactly parallel to your index finger nor exactly anti-parallel to your index finger. It just has to be somewhere along that direction. And then the answer to the cross product would be point in the direction of your right thumb. Okay. So F is perpendicular to the vector QV and perpendicular to B. Okay, so that should already tell you that you definitely cannot cause a particle to speed up or slow down as a result of the magnetic force, because obviously the force is going to go perpendicular to the velocity, and therefore it can't speed it up or slow it down. It can only turn it. There's another force as well. I usually use the differential just to make it make sense. So I'll say the differential force is equal to a current carrying, imagine a current carrying wire carrying a current I. Imagine a little differential length element dl that's parallel to that current I. And if you want to find the force on that current carrying wire, you're going to take a cross product of IDL and B. If you look at the units of QV and the units of IDL, you'll see they're the same. And from that, you probably figure out that these are really more or less the same equations. In this case, we also reach the conclusion that F is perpendicular to IDL. In other words, it's perpendicular to the wire and perpendicular to the magnetic field again. Okay, and we know how to do cross products with determinants of matrices and all that good stuff. So that's all well and good. I would tell you, for instance, here's one quick example. Let's imagine a coordinate system on the surface of the Earth. Okay. Let's imagine this is the eastern direction. This is the northern direction. This is the southern direction. And this is west. And then what I'll say is this direction right here is the altitude. Now, if I imagine a positive particle moving upward, that's its velocity, and it has a magnetic field, I'm going to use, no, I don't want to use that color. I'm going to use red for the magnetic field. So the magnetic field is pointing due east. So from that, you can say QV, which since it's positive, QV is also pointing upward. If it was a negative charge, QV would be pointing downward. But I can take QV, and now I turn this finger, or turn this whole hand until this finger points in the direction of B, which is like that. Now I see that my force is actually pointing into the screen, which is the northern direction. So what I'm going to do is I'm going to say the force on this particle points north. Okay. Now let's try just one more. I'm going to do a negative charge this time just so you get the hang of this stuff. Let's say we have, I don't want to use that color. I think I want to use this color. Whoa. I think I want to use this color. So now let's imagine I've got a negative particle moving south. So this is the velocity. Let's say I have a magnetic field again pointing to the east. And now QV points to the north, not to the south. So I put my index finger towards the screen, and then I turn my hand until my middle finger can actually point in the direction of B. In this case, I see that now my middle finger is pointing in the direction of B. I've got QV pointing in the northward direction, and my force is actually in a downward direction. So now I'm going to use a black vector to say that this is the force on the negative particle is downward. Okay, so there's two nice examples of showing you how to do that. Now that we have that, I'm going to move on to, because I think I've given you more than enough to use those force equations between this and all the cross products we've been doing for 2 semesters. But now I'm going to go to the law of Biot-Savart and show you a quick example of that. Specifically, I'm going to show that this is, in fact, the electric or the magnetic field created by a current carrying wire that's infinitely long. So let's do that. So again, I'm going to draw a coordinate system. This coordinate system is drawn like this. And I'm going to imagine that a third dimension, of course, comes out of the screen like this. And I'm going to label these axes. That's my x-axis. That's my y-axis. And that's my z-axis. Now I'm going to draw a current carrying wire. I'm going to try to draw it really small and thin because it's not supposed to have much physical size compared to the dimensions that we're using. And of course, this is always a problem because it wants to try to correct my drawing by making it connect to something that it's not supposed to connect to. Okay, so that's my current carrying wire. Notice it is again parallel to the z-axis, and we're going to assume that it goes to infinity. Remember, in a physics world, going to infinity might mean that if I'm 1 meter away, then the end of it has to be at least 10 meters away. I personally prefer a factor of 100, but a factor of 10 is really usually enough. So that's what we mean by infinitely long. We don't want to examine points closer to it than 1/10 of its length, that sort of thing. Okay. I'm also going to say that the current is going up. So I points upward. And what I'd like to know is, though it's on the y-axis, I'm going to say right here is a distance r, because obviously the formula I had was B equals mu 0 I over 2 pi r. So I'm going to use that distance to be r, and I would like to figure out what the magnetic field is right there. So this point is the point P that we've been talking about. Okay. So the law of Biot-Savart is the following. It says dB is equal to mu 0 I over 4 pi. Well, I should leave that integral off. Times GL cross RP minus RDL divided by the magnitude of RP minus RDL to the third power. Well, that was really bad. Let me fix that. Make sure everybody knows that's a 3. It just kept getting worse and worse and worse the more I drew. All right, so now I've got to go about figuring out what all these vectors are, what all these quantities are. So DL is supposed to be a differential line element that is a vector, and it points in the direction of current. So what I'm going to do is I'm going to imagine this little bit right here as a length, and then I will make the DL vector is going to be equal to dz k hat. Okay, so its length is dz. Its direction is the positive k hat direction because the current's going that direction. And in fact, you might realize that this distance right here, since it happens to be parallel to the z-axis, is in fact z. Just like this distance right here, which happens to be parallel to the y-axis. But in this case, I'm calling that distance r because I wanted the formula to come out in terms of r instead of y. Okay, so now I need a vector that points to P. Anybody have any idea what the vector RP is? Remember, it points from the origin to the point P at which we wish to know the magnetic field. I'm going to draw the vector on here, and maybe hopefully that will give you a better idea of exactly what the vector is supposed to look like. I think I'm going to use this blue color here. So that's the vector RP. Now, can anybody tell me what RP is? I bet you Carter can.
Is it J?
J is definitely the direction, but what would be the magnitude? How long is it?
Is it R?
Exactly. Good job. Good job, Tanika. RJ hat is all you got to write. Does that make sense? See, it seems really complicated and it's scary, but it's really not. It's just, hey, I'm looking for a vector. I need its length. I need its direction. That's all you need. Now I'm going to draw another vector for RDL. This vector I'm going to make green. So that's the vector RDL right there. Anybody want to take a guess as to what RDL is? Anybody know its magnitude or its direction or both? I bet you Tanika might have this one if Carter don't. Maybe Javanya too.
Just R again.
Yes, not R this time. I specifically called it Z because it happens to be along the Z axis. But yeah, you're thinking right. What about the direction, Carter?
K hat.
Exactly. Okay. So does anybody recall from this right here? Remember the right-hand rule I taught you for finding out what direction the magnetic field should point? In which direction should the magnetic field point at P right there? Anybody know? Answers are in the board, out of the board, up, down, to the right, to the left. Anyone? It's okay if you don't. We'll
Is
figure
it
it out in a
down?
second. It should actually point into the screen. I think I heard you say out, but it should point into the screen because you got to put your right thumb along the positive Z direction and you got to wrap your fingers around and then you got to say, in which direction would my cooked spaghetti noodle fingers be pointing at that particular point B? And if you cut the actual noodle there, you would see that the cross section of the noodle is opening towards the back of the screen, towards behind the screen. So that's the direction of it. Does that make sense to everyone? This is Rust. I mean, this is something that I just introduced to you. So I don't expect you to get it immediately right now, but with time, you're going to. So don't feel bad if you didn't get it right now, but that's how it should work. All right. Now that I've got RP and RDL, I can go ahead and compute RP minus RDL so that I can find its magnitude. And I think you all realize that that should be RJ hat minus Z K hat. Now, it's RP minus RDL, so I'm going to use a red vector to draw that actual vector just to make sure it stands out really well. That is your vector RP minus RDL. Looking at that, I suspect y'all can, without any work, figure out exactly what the magnitude of RP minus RDL is. Anyone want to take that? I'll give you a hint. PYT. Give you another hint. PYTH. PYTHA. PYTHAG. All right, it's going to be R squared plus Z squared square root. Okay, because notice it's just a right triangle made out of the green vector and the blue vector, and the hypotenuse is RP minus RDL. So now we're ready to actually compute all this scary, scary stuff. So what I'm going to do is I'm going to say B is equal to the integral of dB, which equals mu 0 I over 4 pi times the integral of dl. Now, what we said was dl is dz k hat. And now I've got to take a cross product of that with r j hat minus z k hat, like that. And then I got to divide all this by r squared plus z squared to the 3/2 power, because it'd be to the cube power, but it's already a square root, so we made it 3/2. Does that make sense to everyone? Now I can simplify this a little bit. I'm going to recognize that this part right here, whoa, Nelly, I hate it when it does this. This part right here, the numerator, that's actually dz k hat cross r j hat minus, I'll put parentheses, well, I should have put parentheses around it, minus dz k hat cross z k hat. And the reason why I do it this way is I want you to see that this part, ooh, there I go again. This part is 0 because it's k hat cross k hat. And remember the formula for a cross product, A cross B magnitude is equal to the magnitude of A times the magnitude of B times the sine of the angle between them. In this case, the angle is 90 degrees. Okay, or excuse me, 0 degrees, stupid head. In this case, the angle is 0 degrees because it's k hat and k hat, right? So what I'm going to do is I can drop off that second term, and what I'm going to have now is mu 0 I over 4 pi integral. Now I'm going to use the linearity of the cross product, which basically says that I can pull all the scalar parts out in front, and I'm going to get dz times r times k hat cross j hat. Now, if you look at k hat cross j hat, you will see that that points in the negative x hat direction or negative I hat direction. So k hat cross j hat is just negative I hat, which is exactly the direction we said. We said it would point towards the back of behind the screen. And that's exactly what it did. So now I have, in addition to that little thing, I have z squared plus r squared to the 3/2 power. And this is going to be, I'm going to use the r and the I hat and pull that out in front. I now have a negative mu 0 I r over 4 pi I hat integral of dz over z squared plus r squared to the 3/2. And what I'm going to do is I'm going to let r equal z tangent theta, then dr would equal z secant squared theta d theta. Okay, so now I have negative mu 0 I r over 4 pi I hat integral. dz is going to become, or excuse me, I did it wrong. I did it backwards. Sorry about that. Let's fix this real quick. That's the problem with working with symbols. Sometimes you forget which one's the symbols and which one's the actual known quantities. In this case, what I'm really integrating with respect to is obviously the z's. So I want to say let z equal r tangent theta. I said it exactly backwards. Hopefully y'all might have caught me on that and just not said anything because you weren't that sure. That's fine. I don't mind you saying anything, but I should not have made that mistake. Now I can say dz is equal to r secant squared theta d theta, and that's just from the derivative of tangent. And I know that looked really bad, so I'm trying to write it a little better. So this is secant squared theta, like that. So now what I can do is make the top into another r, oops, it was supposed to be r secant squared theta, d theta. Now, in addition to that, I'm going to take and make the bottom into a pair of square brackets. And I think you all can realize I'm now going to have a common factor of r squared. So I'm going to pull out that r squared, and that's going to leave me tangent squared theta plus 1. And of course, all that still raised to the 3/2 power. So now what you can see is that r squared raised to the 3/2 in the bottom, that's going to become r cubed in the bottom. And the two r's on top is going to become r squared on top. So I end up having r squared over r cubed, which is just 1 over r, basically. So now my next line is going to be negative mu 0 I hat over 4 pi r, because that's all that was left, times the integral of secant squared theta d theta. But what we know is 1 plus tangent squared is secant squared. So now I've got secant squared theta raised to the 3/2 power. And of course, that means I'm going to have secant cubed in the bottom and secant squared on top, which leaves me just a secant in the bottom, which is the same thing as a cosine in the top. So I can now say negative mu 0 I over 4 pi r I hat integral cosine theta d theta. And if you'll notice from the substitution I did, that was z is equal to r tangent theta. That tells us that the very theta we're talking about is this guy. Okay. So because of that, we know that we technically be integrating from theta approaching negative 90 to positive 90 degrees, or pi over 2, either one, that's fine. But that's basically what we're doing. Now, this is an even function, so we could just multiply by 2 and then integrate that from 0 to 90. But no big deal. It doesn't matter either way, whichever way you choose to do it. Now what I'm going to have is the derivative of sine is cosine, so the integral of cosine is sine. So now I have negative mu 0 I hat over 4 pi r times the sine of 90 degrees minus the sine of negative 90 degrees. And of course, the sine of 90 is equal to 1, and the sine of negative 90 is equal to negative 1. So I get 1 minus negative 1, which is 2. So the ultimate result is just going to cancel out the 4 in the bottom to leave a 2. So I get negative mu 0 I over 2 pi r in the I hat direction, which suggests B is actually equal to mu 0 I over 2 pi r in the theta hat direction. Which, because if you imagine rotating this axis about the z-axis, what you would see is slowly as you rotate it, you would run eventually into the r being on the actual x-axis. And in that case, it points in the negative y direction, and you could keep turning it, and you'd always see that it always points into the screen. Well, that's the very definition of the theta hat direction, as I showed you in this diagram right here. Any questions on that? I'll just say again, theta hat is equal to negative sine theta I hat plus cosine theta j hat. So that's where that is. Any questions on that one? All right, there's another. Well, let me show you how quickly and easily this can be done with Ampere's law. So Ampere's law before the correction is the closed integral of b dot dl is equal to mu 0 times I enclosed. Okay. So what we're imagining here is we're trying to imagine a closed path, not a closed surface like we did with Gauss's law. This is a b dot dl. So this is a line or a path integral. So we're trying to make a closed path. That means something that can go off in space and do all these crazy directions. But the main thing is it has to return to its initial point at the end. Now, once you make that closed path, then what this actually applies to is on the right-hand side, we're looking for all the currents that actually penetrate any surface that could be spanned by that actual circuit. So we're making a path. A path might look like, for instance, this. Okay, that's just a closed loop. You can imagine, for instance, if you made that closed loop out of a wire like a coat hanger, then you could dip that coat hanger wire into a solution of dishwashing detergent, water, and a little bit of glycerin, and then slowly lift it out, and you would actually have a flat bubble across the surface of it, just like this. Well, that flat bubble is in fact one surface bound by the path, the closed path C. So I could put a C there and just say closed path C. Okay. Now that bubble surface, that flat one's perfectly fine, but it's not the only one. In fact, anything that could be used as a surface that has its outer boundary as just that red line is also a valid surface. So you could imagine that red line, for instance, being the opening of Santa Claus's bag. Then the whole surface of Santa Claus's bag would be would span the actual curve. So that surface is also a valid one. Everybody sort of seeing what I'm talking about there? Dang it, that's stupid. So we could even imagine, to make sure you understand this in 3D, like that. So yeah, that flat surface of bubble would work, but also all these other ones would work. That detail is exactly what Maxwell saw and was able to fix Ampere's law with. But right now we're not worried about that so much as we're worried about the loop. So we've got to imagine a loop. And remember when we did Gauss's law, the closed integral of E dot dA, we chose a surface on which the electric field was constant, i.e. an equal potential surface, or was in fact the electric field perpendicular to that surface, because the perpendicular parts to that surface, well, I should say are, and which is the same thing as and with, when you actually have the electric field perpendicular to a surface, that surface is a equal potential surface. But when you have the electric field that sort of uh, parallel to that surface, then the dot product E dot dA is going to give you 0, because the dot product is supposed to bring out only the components of E and dA that are parallel. So the dA is defined to point perpendicular to the surface. So in this case, we're trying to find a loop that would be have a constant magnetic field strength on it, and use that to find out what the magnetic field is for a given configuration. So that's Ampere's law. Now let me show you how we use it. So I'm going to draw another coordinate system again, just like I did before, but it's going to be a lot less complicated, because all I need is a wire like this. And now with a wire like this, I have experience from the law of Biot-Savart to say that my hypothesis, let's say hypothesis, is that the magnetic field is equal to some B that depends only on R. So I'm saying its magnitude should only depend on the perpendicular distance from the center of the wire, and that it points in the theta hat direction. Again, I'm going on the assumption that the current is going up, and that's the positive Z axis. So I can also do this and this. This would be my X axis, that would be my Y axis, and that would be my Z axis. So making that hypothesis, I can now say left-hand side. And the left-hand side is the closed integral of B dot dl. And that's going to be something I can work out when I figure out exactly what contour, what path I want to integrate around. Now, what I know is we define I such that if you take and curl your fingers around with your right hand now, curl your fingers around a loop of wire in the direction that your right fingers are going, then your right thumb points in the direction of a positive current. So I am going to imagine a loop that is circular. In fact, it's exactly the same circle that I put right here. Remember that dark blue circle? That's what I want. I want to make that dark blue circle around this wire. I'll do it in red this time, though. So I'm going to say that I'm going to go and integrate around this way. So in order to do that, I've got to imagine a little line segment of the wire, or excuse me, of the contour, DL. And in fact, DL is going to be equal to, if I call this the radius R, it's going to be equal to R d theta, where that's theta, and it's going to point in the theta hat direction, just like the magnetic field does. So now the left-hand side can become integral B of R theta hat dotted with R d theta hat. Now I'm going to use the linearity of the dot product to put all the scalars out in front, and I'm going to get B of R times d theta times theta hat dot theta hat, which is equal to, of course, just 1, because it's the magnitude of theta hat, which is 1, times the magnitude of theta hat, which is 1, times the cosine of the angle between them, and the angle between them 0, and the cosine of 0 is 1. So now what we get is the left-hand side becomes B of R d theta, but we're on a circle whose radius is fixed. So B of R and R are both constants. So we get just the integral of d theta from theta equals 0 to 2 pi. So ultimately we get 2 pi r, 2 pi r times B of R. Now the right-hand side, which is the one that has the potential of being easy, but notice the left-hand side is always going to be some length times a magnetic field, maybe plus some zeros, or maybe plus some other terms with lengths and magnetic field magnitudes, but that's all the left-hand side is ever going to be. The right-hand side is mu 0 times I enclosed, and the only I that pierces any of those surfaces is the I that we see. So the right-hand side just becomes mu 0 I. Now we take left-hand side equals right-hand side, and I know we're about out of time. We just hit the mark. Let me finish this up and we'll kill it. What we have is 2 pi r B of R is equal to mu 0 I. So finally, using our hypothesis, we know that B is equal to mu 0 I over 2 pi r theta hat, which is exactly the same result we got using the law of Biot-Savart. So now I've shown you a use of Ampere's law. There's only 3 uses. You can use it for a solenoid, you can use it for an infinitely long wire, and you can use it for a torus. But those are the only 3 uses. Your book has those examples. You need to memorize those 3 examples. I just showed you one of them, but you can also look at my YouTube channel to find how to do those as well. And I'm going to show you next time. I'll show you how to use the law of Biot-Savart to do something special, like finding the magnetic field at the center of an arc of current. Okay. So we're done for today. Don't forget all those notes that I put at the beginning. This will be, of course, in your Google Docs, so you can download these notes as well. But this video is also going to be posted in a few minutes, so you guys are free to go. Make sure you get started doing your final or your face-to-face test redos, all 3 of them. Make sure you do your face-to-face final test. Make sure you do your online final test. Both of those I've moved back to be due by Thursday. And you guys are free to go. Don't forget to chat me your first and last name if you didn't already. I think you already did, but anyways. Thanks everyone for coming.
I have a quick question about the online test, if you have a minute.
Yes.
So I took it, I believe, Sunday night. There were only 2 questions, and I got both of them right, I think, the second time. But my grade in the grade book says a 4 out of 100.
Yeah, you missed the beginning. Basically, there's been something, or you should one, I would have hoped you'd let me know, but evidently the test did not make like it's supposed to. When I pull questions in, it sometimes fills those questions in like it's supposed to, other times it doesn't. But 2 students did send me a message. I got that today, so I'm going to open it now, and it'll be fixed. And I've given everybody till Thursday to get that done. So you can still redo it. I have to make a new one basically, but you have until Thursday to get that one done.
Okay, alrighty. So I'll just look
Sorry,
the new
Hannah.
one. And then yes, I did miss the beginning, but the business side of stuff will be posted to on your YouTube channel, or
Yes,
just
yes.
okay.
All that
Alright.
stuff will be in the very beginning, and I put a lot of notes in there as well. So you had it in writing, even though it's not necessarily the
Perfect.
best of writing. But yeah, it's all there.
Alrighty, I will go watch that. Thank you so much.
All right, you have a good one, Hannah.
Have a good one.
Carter, Micah, y'all have any questions?
Yeah, just a quick one. I just wanted to verify you got my messages in regards to the conversation we had last week about the test.
Yes. Let me double check that. Did you send it by text or?
Yeah, I texted you. I just wanted to let you know I'm gonna have a different supervisor.
Oh yeah, I think I did
oversee it.
remember getting that.
Yeah. Mhm.
Yeah, gotcha. No problem. And did I already send him the questions? I think I did before the break.
So that was my other supervisor, but she is not back from her break.
Okay.
So I'm gonna have a different one of my different supervisors oversee it.
Gotcha.
Mhm.
Does your number end in 1085?
Yes, sir.
Okay. Yeah, I got you. All right, I'll go ahead and take care of that and send the other person that as well.
Okay.
I did push the due date back till Thursday at 11:59 p.m.
Okay.
Okay.
Yeah.
Thanks. Have a good one, Micah.
You as well.
I was gonna ask, what do you need, either for me to set up the online test, like to get a passcode from you, or to get a, like my superior as a proctor?
Gotcha. Are you? Let me see here.